And so TechnicVR is this program here. It's the yellow icon in the suite of programs. There's already a walkthrough for TomoVR and a walkthrough for Projection VR. So today I'm just going to be doing TechnicVR. So I'm going to run up TechnicVR by double-clicking on it. Okay, so TechnicVR gives you this screen, and what I'll do is I'll make that full screen. So there are three parts to the screen. So you get the one part of the screen over here on the left-hand side, which gives you some quick win procedures. So you can click on some of these and you'll get automatic parameters put into the simulation for that particular procedure. So the procedures here range from mammograms to CT scans and general fluoro and dental work and X-ray. So a whole range of different radiological procedures. Now, in the middle, this is the main output of TechnicVR. You get a graph, and that graph shows you the X-ray beam, or a representation of the X-ray beam. So we've got photon energy along the x-axis here, and we've got the photon fluence, or the number of photons per unit area. So this gives us a distribution of photons of various energies within the beam, and the numbers that are made up, that the beam is made up of each energy type. Okay, and then on the right hand side we've got beam outputs, and these are measures or indicators of the X-ray beam that are used in this box. And then we've also got the heat management data. So this is the actual heat in the X-ray tube itself, either on the focal track or the whole anode disc. We also have an output here for the dose area product of the beam. Okay. So in this pad here, in this part of the screen here, we've actually got 4 tabs. So the procedures, so choice of procedure is the first tab that's open, and by clicking on that you can see that we can get different graphs. We've got the equipment tab, and the equipment tab, depending on the procedure that you've selected, the equipment tab will have certain settings on it. So we can do make certain settings or set up the equipment using this tab. So for example, if our equipment was single phase, then we can change the voltage waveform, and it will model the same parameters settings, but using a single phase full wave or single wave phase half wave rectified electrical supply to the generator, for example. If you're in a different jurisdiction, then you can change the frequency from 50 to 60 Hertz, and that will make some changes to the outputs of the X-ray beam. And we can also decide here what controls we have on the control console. So if we only want to, as in most cases, most control consoles only supply you with the option to change the tube voltage and the tube charge, so the kVp and the MAS. Whereas if we click on 3-knob control, then we can change the tube voltage, the tube current, and the exposure time. So we can change 3 controls, so the KV, the MA, and the time, yes, separately. That's really useful when you're looking at the effect of the exposure on the X-ray tube filament and on the heating track, the anode heating. We can also change the filtration in the beam on this pane, so you can see how I can pick materials to filter the beam. So I could pick a tantalum filter here, for example, which will have a dramatic impact on the amount of radiation leaving. So it's normally set to aluminium. And we can also add, so we can keep the aluminium in, and then we could add some copper, for example, as the filter material, and see the effect of that. Okay. And finally, we can age our X-ray tube, so we can make our tube older. The rigours of wear and tear on the tube actually have an impact on the amount of output the tube generates. So we can actually model that as well. So that's all under the Equipment tab. The Exposure tab. So in the Exposure tab, we actually get the ability to change the voltage and change the charge. As I said, we can either change the charge as a single parameter, as in here, or if we go back to the Equipment tab and change it to 3 knob, then we can change the charge as current and time independently, and it gives us the tube charge here as an output. So just go back and change that to 2 knob again. On this one, we can also change the focal spot size, which changes the filament load, obviously because it's a different filament, and it also changes the heating. It'll change some of the heating characteristics. This output here is the filament load output, so this is quite useful because, for example, this exposure of 88 tube voltage of 88,000 volts and a tube charge of 4 milliamp seconds. If we go to the Equipment tab, make that into a 3 knob control. So it was 4.4, wasn't it? So we could do that. At the moment, that's giving a 5.1 amp filament load. And if we were to drop the tube current to 100 and increase the exposure time to 44 seconds or 45 seconds, then we can actually get the same tube charge at the same tube voltage for 4.7 amps of filament load instead of 5.1 amps of filament load, which takes us, doesn't wear the filament out so quickly. So we can model these comparisons. Okay, so finally on this tab we've got the Dosimetry tab. So this graph is made up of, and all of these outputs here are made up from fictional outputs of a detector in the beam, and that detector is on the surface of a patient. So we've got here the patient thickness at 30 centimeters and the source image distance 180 centimeters, and we've got the location of the detector in the plane of the imaging plane in relation to the anode. Okay, so I can also open and close the collimation of the beam, which will affect the dose area product. So so if I open the collimation right wide and I reduce the source image distance, then you can see that we're actually getting a lot more radiation at our detector because the detector is not as far away from the source. If we reduce our patient thickness though, then the detector moves further away again because the detector's on the surface of the patient. So by fiddling with this, I can set up a particular patient scenario, say for example on the kneecap at 100 centimeters source image distance, the knee is perhaps 15 centimeters thick, so our detector is actually at the surface of the skin there. And then what I can do is I can drag the detector towards the foot perhaps, and towards the head perhaps, and show the anode heel effect here. So we can show that when the detector is at the heel of the anode towards the negative, towards the positive terminal, then we get less radiation than when it's towards the negative terminal. So we can actually mimic that as well. Okay. So I'm just going to expose this beam. So it's a general chest X-ray. So I'm going to go into the exposure tab and I'm going to hit the expose button. And nothing seems to have changed apart from we have a calculation of dose area product. But in this box at the bottom here, if I click on the box, now I can actually open up that exposed beam, and then I can select that as our reference point. And now when I make changes, you'll see that the exposed beam is in red, and we can compare that beam with any subsequent beam that we set up. So that's very useful to identify the changes. This the beam will stay in, the graph will actually be in this format no matter how much we change. So if I was to increase the tube current and the MA, the kV, the tube voltage, then it now goes off the graph. So what we need to be able to do is move the axes of the graph. And so on this slider here, I can actually drag the axes of the graph down and across so that I can actually now see the new settings against the default settings that I had set before. This is very useful for when we're comparing, say for example this is a chest X-ray, if we wanted to compare that with a mammogram. So if I hit the mammogram craniocaudal, so this is the default chest X-ray setting, and now if I change the graph axes, I can now see the mammogram exposure against the chest X-ray exposure. So they're the basics of the system. Now there are some more things we can do up here on the tool menu. I've got the ability, if I click the file, to export the output. So I can either save that. So now I've set that up, I could save that as a graphic. So if I click Save Graphic, click Desktop, call this Mammogram versus Chest X-ray, and save that. Now on my desktop, I'll have an image which I can open up, and I could put that into a PowerPoint, for example. And it shows me that the red beam is an 88 kV by 4.5 MAS beam. And the black one is just off the screen there because I can't quite work out how to use Windows Viewer, Image Viewer, but it would show us both if I put that into a PowerPoint. Let's just do that. And then File, Insert Picture. There you go. So now I've got mammography with a molybdenum target rhodium filter 28 kV P71 MAS versus a chest X-ray 88 kV and 4.5 MAS. So that's a nice illustrative slide for a PowerPoint, or you might want to give the students a task to make something like that. So next, going back to TechnicVR, I can also export the data rather than just the graphic. So if I save the data, it calls it, so we'll call this Mammo. So it's going to save the black data, I think. So I'll call that Mammogram. And it saves it as a CSV file. So if I save that, now if I open that in Excel by double clicking, then I actually have the Mammogram output, and it gives me some basic numbers. It gives me all of the information that was actually presented as the summary data for the tube, for the exposure, for the beam, and then it gives me a count of each number of photons for each energy bin for the whole spectrum. So if you were doing some research, then this would be a good way of getting the spectrum that you wanted to then put into your new whatever you're using it for. Okay, so going back to the screen, so that was file. So you'll notice that when you hover over something, then you get a tooltip. Yep, so this comes up to show you what things are. So they usually no bother, but if you don't like them, then you can, in the settings, you can actually get rid of them, and you can actually make the delay longer or shorter depending on whether you want to read them or not. Okay, spectroscope. So we call this plot in the middle of the output window the spectroscope, and we can change that. So we can have it with no background, we can have it with a color background behind, so that we can use the analogy to white light. So white light is a mixture of different colored lights, different energies of electromagnetic radiation that make up the rainbow, if you like. And so what we can do here is we can put that on the background so that we can use that analogy. So we can say, well, in the world of X-ray, X-rays are very much like white light in that they're a mixture of all different energies of X-ray photons, and the mammograms are more towards the low energy range, which is like in light terms would be the red end, whereas the chest X-ray is more towards the middle, which is the yellows and greens, and nothing in this case is in the blue area. But if we use high kV technique, then we're actually bringing in a lot of these high energy photons into the beam. So for example, a CT scan, if I drag that axis back down again, you notice that the CT scan setting at 120,000 volts is actually getting some photons in the blue spectrum, the blue part of the spectrum, or the high energy part of the spectrum. Okay. So that's the spectroscope. We can also have a scenario where we just show the color of the actual beam itself. This is quite nice because it shows the characteristic radiation lines for the given target. So this is a molybdenum target, so we have the K lines. The characteristic radiations are very different from the tungsten target, which is got characteristic radiations in a much higher part of the spectrum. So if I pick a general X-ray, then we've got green characteristic lines of emission for a tungsten target. And the final one is we can do that with a black background, so we can actually see the lines, characteristic lines showing up in a black background. And we can also take the plot lines away so that you just get the color. which is quite nice. So if we now go and change the tube voltage, and increase the tube voltage, then we can actually see the effect in sort of false color. Which is quite cool. So go back to our standard settings. Okay, now over here we have a whole range of different outputs. Some of these are very commonly referred to in journals. So the half value layer, for example, in millimeters of aluminium of the beam is a way of identifying how much penetration the beam has. So this particular beam at 77 kV has a half value layer of 1, 3 millimeters of aluminium. So that means that 3 millimeters of aluminium would halve the actual amount of dose. So what if we increase the tube voltage to 100? Now the half value layer is 4 millimeters of aluminium. So this is a much more penetrating beam. And in fact, the beam penetration, which if you hover over it, the tooltip will tell you what it is, which is the percentage of primary photons exiting 10 centimeters of soft tissue. So 8% would actually exit soft tissue with this beam at 100 kV. Whereas if you drop that down to something like 50 kV, then the beam penetration drops to 3%. And the half value layer is nearer 2 mils of aluminium. Irradiance is just the power incident on the surface of the object. The mean energy of the beam is 33 keV, and the median is also 33 keV, and the effective energy is about 28 keV. So the output per microgray per MAS, the microgray output per MAS is 51 for this beam. Now if we go back and age our machine, so this is a brand new machine and it's giving us an output of 51 microgray per MAS for this particular exposure. But what about when the tube's about 5 or 10 years old? Then it's aged and you'll find that the output per MAS is now only 31. So the same setting on the machine will give you far less radiation. So you'd have to change the settings. So you can't stick with standard settings over the lifetime of the tube. You've got to change them every so often, depending on the QA results. Now we can actually change this output because this is all a lot of data, but if you know what you want, then you can customize that display. So here we have the default settings. So if I know that I'm only interested in half value layer, well, what I could do is I could just say I don't want to see any of them. I don't want to see the heat, I don't want to see the timer, and I don't want to see the DAP. So that will now just eradicate that side, that whole section. So I've got a much simpler proposition. But if I do want to see things, say for example I want to see the heat and the beam output, but I don't want to see all of this beam output. I just want to see the dose and the half value layer. So I can take all the rest out. So now I've got the heat and just 3 numbers, which will do me fine. So you can fiddle on with this to get it to how you want it to be for a given purpose. It will remember that, so next time you log in on that particular computer, it will be in that format. So if you do that on a shared computer, then your colleagues might wonder what's happened. So you maybe have a policy where you always leave it how you expect to see it. something like that. And then if you click on the help, that one doesn't work on this particular model. Let me just, there is a help file. I'll just close this one down and fire up the local copy of this. Go on the help file. So exactly the same. The help file will actually give you quite a lot of information about assumptions in the model, and quite a lot of description of each of these outputs, for example. So half value layer, it will tell you what half value layer is and what we're actually presenting you back to. Something like intensity, for example, tells you what intensity means, so that's really useful. We also have validation, the references for all the work that's gone in behind the scenes. So this is these are all the sources that we've used to come up with the most accurate model. Scatter, for example, how we've actually put scatter into the model, the entrance surface dose, what things you can assume that are modelled and what things are left out of the model. Okay, so lots and lots of information within the help file. So that's it really. This is the end of this video. I'm going to show how we can actually use this to answer certain questions that students might have concerning certain optimization strategies in later videos, but not in this video. Thank you very much.